Hello, friends. So yesterday we briefly talked about how language models size has increased dramatically over the past few years and why we need a more practical approach. So in terms of financial cost, GPT-3, for example, allegedly costed a couple of millions to train. In terms of practicality, ultimately we want our end users to be able to use the models in their devices, in their mobile phones. So the resource is constrained. And we also talked about, in terms of environmental impact, on how we want to look at the models, how we want to train the models and inference the models sustainably and efficiently. Now, in terms of techniques people use for models compressions, here are some of the metrics to benchmark the efficiency. For example, the size of the parameter, floating points, operations per second, latency, etc., etc. And in terms of how we go about doing that, here's a list of techniques. Quantization deals with scaling and shifting the weights. So, for example, if we've got the weight stored in 32 bits, then we can reduce it to 8 bits. Now, that's 4 times reducing the size immediately, but obviously it comes at a performance cost of the model. And if we want to go further, we can reduce even further from 32 bits to bits. So that will be from 32 to 1, which is 32 times. Pruning concerns with removing part of the network. So for example, we can be removing some weights, we can be removing some layers, we can be removing even some components of the architecture. In terms of knowledge distillation, the most common one is the teacher-student model, where we train normally a slower model, which we call the teacher model, and then subsequently use that to teach a smaller model as the student model by using the output of the teacher model. In terms of architectural change, what we can do is first benchmark the different performance of different layers, and then we can identify where the bottleneck is and perhaps change part of the network using different techniques. For example, in the paper Squeeze Spurt, the author replaced part of the network from the fully connected feed-forward layer to using group convolution, and it ended up in a speed up of 4.3 times. In terms of low-rank factorization, we decompose the matrix into multiple matrices and then take the top-performing matrix. In terms of parameter sharing, we have different components within the model to share the same weights. So effectively we reduce the number of weights and the size of the model. And lastly, very often it's very easy to start of the problem to just go straight to the state-of-the-art model. But in practical terms, we want to ask ourselves, do we really need the state-of-the-art model? And very often a simpler model will just have enough performance for the job. And so yeah, these are the different techniques people use in terms of model compression. And I hope you find that useful.